In the last segment, we focused on some of the fundamentals of drawing resonance structures. Those were different ways to show the electron arrangements around atoms in two otherwise identical structures, structures that have the same arrangement of atoms within the molecule, the same positions of the single bonds within the molecule, and they differ only in the locations of the pi bonds and the lone pair electrons. So we're showing that lone pair electrons and pi bonds aren't necessarily fixed into place, but instead the actual electron arrangement of a molecule is a hybrid or an average of the different ways that we can represent the molecule by showing different Lewis structures. So in actuality, any one Lewis structure doesn't accurately reflect the structure of the molecule in terms of where its electrons are located. Instead, the actual structure is an average of the different resonance forms that we can draw, where any one resonance form never accurately shows the molecule at any given point in time, but instead it just shows one of the contributing structures toward the actual hybrid structure of the molecule. So when we think about the different resonance structures and their relative contributions toward the actual electron arrangement of the molecule, not all resonance structures are created equal. Some of those are going to be major contributors, meaning that when we think about their contribution toward the overall hybrid structure, the hybrid structure is going to look an awful lot like some of the structures and not so much like other structures that we could draw, not so much like other resonance structures that we could draw. So how do we go about determining which are going to be the minor versus major contributors when we're looking at and comparing and contrasting resonance structures? Because we need to be able to do that in order to determine which structure is going to most accurately reflect and allow us to predict the different properties of the molecule. So what we're going to do in order to determine major versus minor resonance contributors and rank the different structures that we can draw in terms of how much or how little they're going to contribute toward the actual hybrid structure of the molecules, we're going to look at the following four criteria. And the key point here is that we need to look at these following four criteria in order. So the top criteria is the most important in determining the actual major hybrid structure. And point number four, as we go down the list, is going to be the least important consideration. So when we're comparing two structures, if we see that one of them is superior to the other by point number one, we can stop right there and say that we've assessed and determined what is the major contributing structure, because point number one there, having an octet or more atoms is preferred, is the most important factor. Even if all the other factors in this list are better for one structure than the other, as whichever structure has the complete octet is going to be the winner. So as soon as we determine that one structure has an octet, the other one doesn't, the one with the octet is automatically the winner. You don't even need to go any further down the list to compare and contrast the structures. So we're following these in order until we find one on the list that allows us to differentiate between the two structures, the two resonance forms that we're comparing. So first and foremost, when we're thinking about these in order, the main contributing factor toward determining how important a resonance structure is, toward looking at what the actual molecular structure looks like, is that having an octet on more atoms is preferred. The more atoms that have an octet, the better. So if you have a structure where every single atom in the structure has an octet, and another structure where one of the atoms is missing an octet, the one that has an octet on all the atoms is going to be the major resonance structure. The other one's going to be the minor structure. Point number two, a larger number of covalent bonds is preferred. So as we're looking at the structures, if we see that one structure has a total of 5 covalent bonds and the other one has a total of 6 covalent bonds, the one with 6 covalent bonds is going to be the preferred structure. Do keep in mind though, when you're thinking about larger number of covalent bonds being better, you can never exceed the octet rule for carbon, nitrogen, oxygen, halogens, which we're representing by X there. You just can't do it. You can be below the octet, but never above the octet. And when we're thinking in terms of stability, a larger number of covalent bonds is preferred as long as you are not over the octet rule with the structure you've drawn. So point number three in comparing resonance structures to one another, if we're comparing two structures to one another and we've looked at criteria 1 and 2 and we saw that both of them have the same number of atoms with an octet, both of them have the same number of covalent bonds, then what we have to do is look at criteria 3 here, which says that structures with fewer atoms that carry formal charges are going to be preferred. So item number 3 here means that we want to try to minimize the number of atoms that have formal charges within them. So that is criteria 3. And then criteria 4 is kind of a follow-up to criteria 3, and that is if we have to have formal charges in the structure, that it's best to have the negative formal charges on the more electronegative atoms, and the positive formal charges on less electronegative atoms. And that comes down to the fact that electronegative atoms are better able to handle having a negative formal charge on them. And so the molecule is going to be more stable if the negative formal charge is on the more electronegative atom. And the positive formal charge is as far away from that electronegative atom as it can possibly be. So keep in mind that these are the criteria and we're following them exactly in order, where as soon as we find one criteria on this list in order that separates or differentiates the two structures, we can stop right there and move on. If you reach the bottom of the list and you realize that you have drawn a structure that is inferior to one or more of the others by every single criteria, then you don't need to show that particular structure, because if it's inferior by every single one of these four criteria to some other structure in the set, it means that that structure that you've drawn is not a significant contributor at all. It would be extremely unstable. So really what we can think of these rules for is rules that govern the stability of the molecules, where the octet is going to be the number one factor that's governing the stability, and then we go down in order from here. And the more stable the resonance structure, the more strongly it's going to contribute toward the actual form. And so if we find a structure that's just bad by all four criteria, we don't want to list that. That structure is going to be extremely high in energy, in other words, extremely unstable. It's not going to be a factor contributing toward the actual electron arrangement of the molecule, so we can ignore that. So now what we're going to do is we're going to do a couple of example problems to look at following these criteria for establishing the relative contributions of different resonance structures. So what we're going to do is we're going to go down and we're going to look at, as our first example problem, the resonance structures that we drew in the last segment for the acetic acid molecule, shown here at the bottom of the page. We drew three different resonance structures in total, and we want to determine what are going to be the major and minor resonance structures for this particular compound. So we're going to rank these resonance structures in order, with number one being the most strongly contributing. So number one we could think of as the major contributor. Number two is second on the list, and number three is going to be the least contributing, the minor contributor. So going through our list here, 1 through 4, following those criteria in order to determine major and minor resonance structures. First off, an octet on more atoms is preferred. So when we look at our three structures here, and we think about whether the atoms all have octets or not, we're going to take a look first at the structure on the far left and ask yourself, is there a complete octet around all the atoms there? Maybe pause for a moment and just look at that. Hit the pause button on the program if you want to think about that. Is there an octet on all of the atoms? The answer is yes, there is. Come to the second structure and we ask ourselves, is there an octet on all of the atoms? And again, when you're asking yourself this question, octet yes or no, it's a good idea to pause the program and make yourself think about this for a moment to ask yourself, is there going to be a complete octet around all the atoms or not? And the answer here is no. There is not an octet around all the atoms. The carbon atom right here in the middle that has that positive formal charge does not have a complete octet. It only has 6 electrons. So there's no octet there. So we can automatically, based on criteria 1, say that the structure on the left is superior to the one in the middle. We come over to the structure on the right and we ask ourselves that same question again. Is there a complete octet around all of the atoms there? And it's a good idea again to test yourself. Ask yourself, is there an octet around all of the atoms here? And the answer is yes, there is. So the one that you may have been wondering about and asking yourself most of all, is there an octet, is this oxygen atom that I put in blue here? There is, because there's 3 covalent bonds. That's 1 to the hydrogen, 2 to the other carbon atom, and then that lone pair of electrons gives us a total of an octet. So both the structure on the far left and far right have an octet. The one in the middle doesn't. And so with that, we can immediately say that the one in the middle has to be the least stable, least strongly contributing of those 3 structures. So then we're going to go down to the next criteria on the list, step 2, because we weren't able to differentiate between the structure on the far left and the far right using just step 1. So step 2 is what we're going to look at next. A larger number of covalent bonds is preferred. And so of these 2 structures, we can count the number of covalent bonds in each of those 2 structures in order to determine which is going to be major versus minor. And in each of those two structures, I see a grand total of the same number of covalent bonds. So in each case, I see 5 covalent bonds. And keep in mind that oxygen-hydrogen bond is the 5th one that I'm counting there. Same thing over here. 5 covalent bonds. So these two structures are equal in terms of their covalent bonds. So then we have to go down to the third criteria on the list, and that's where we're going to be able to tell these two apart in terms of their stability, is based on the third criteria on the list. The third criteria says that structures with fewer formal charges are preferred. So here we have 0 atoms with formal charges. And over here we have 2 atoms with formal charges. And so as a consequence of that, the structure that is going to be the major contributing structure is going to be the one here on the far left, structure number 1. Structure number 2 is the one on the far right, and the least contributing there is structure number 3 in the middle. So we've gone through that list of criteria to come up with what's the major structure and what's the minor contributing structure here for this set of 3 different molecules. So we're going to go through and do the same exercise for another example, but first we do want to ask ourselves, is the structure we've listed as structure number 3 actually going to contribute at all, or is it inferior in every single way to one or more of the other structures, and therefore we shouldn't show it? That was that point that we listed right here in green. So looking at structure number 3, it is inferior based on not having an octet. It is inferior based on not having as many covalent bonds as the other two. It is equal to the structure on the right in terms of having positive and negative formal charges present, in terms of the number of those formal charges that are there. In terms of criteria number 4, the structure in the middle is actually superior to the structure on the far right because of the fact that the negative formal charge is on the more electronegative atom in the middle there, and the positive formal charge is present on the less electronegative atom. So that does, based on criteria 4, make the structure in the middle there, the resonance form in the middle, superior to the one on the right. And so we can go ahead and list it because it's not inferior in every single regard. It's just inferior in some of the regards, which makes it number 3 on the list rather than ranking more highly. So the key thing to keep in mind here as you go through these is go through them in order to rank these. Once you get to the very bottom of the list, look at your 3 structures and particularly which one you've ranked lowest and ask yourself whether that's going to contribute at all. If it's inferior in every single way, it's not going to contribute. If it has at least 1 or 2 points that work in its favor as making it superior, then go ahead and list it. So all 3 of these are significant contributors, but the major contributor is going to be structure number 1. That means that when we think about how we would expect the electron configuration of this molecule to most strongly, which one of these molecules it would most strongly represent, we would expect it to most strongly, the actual structure to most strongly represent this structure number 1, with a second highest contribution from the structure we've deemed as structure number 2, and then least contributing is structure number 3 there is going to be the most minor contributor. So let's do the same exercise for another example. And this other example that we're going to look at should again look familiar to you because it is a structure set that we used as our example for drawing out resonance structures in general. And what we're going to try to do here is we're going to try to go in and rank these in terms of their relative contributions as 1 through 4 here, where 1 is the major contributor, number 4 is the least contributing. So we're going to start off again at the top of this list here, that an octet on more atoms is the preferable situation. So we look at our different structures here and we ask ourselves, is there an octet on these different atoms? So we ask ourselves about this one, and you can pause this and ask yourself, is there an octet on all of the atoms? And you'll find that the answer to that question is yes, there is an octet. Come over to the next one, and the carbon atom right here does not have an octet. So I'm going to put octet and put an X next to it to indicate no octet there. Come over to the next one. This is a CH group because of CH group right here, CH group right here, CH group right there. So that means that carbon only has 3 bonds to it, therefore not an octet. And a little rule of thumb here is that anytime you have a carbocation and a positively charged carbon, there's not going to be an octet on that carbon. So I'll go ahead and mark that off as no octet for that situation on the far right either. So with that in mind, based on just criteria number 1 alone, that is the only criteria we need to determine which of these is the major contributing structure. That's going to be the one on the far left. We'll go ahead and plug in as numero uno. So that's number 1. Then we need to determine what is ranked as 2, 3, and 4. So coming through, ranking number 2, 3, and 4. We're going to go through the criteria in order here. So second item on our list of criteria for determining the relative rank is that a larger number of covalent bonds is preferred as long as we don't exceed the octet rule. So larger number of covalent bonds, we're going to write out how many covalent bonds are in each of these structures that are left here that we haven't yet ranked. So number of covalent bonds in structure, the second structure from the left, is going to be a total of, we have 6 covalent bonds in the ring that are sigma bonds, plus 2 pi bonds would make 8. And then we have a 9th bond coming off the ring, so we have 9 covalent bonds in total. And for the next one, 9 covalent bonds, because we have the same number of pi bonds in each of these situations and the same number of sigma bonds or single bonds in each location. It's a little bit of a tongue twister. So we got that. So number 2 we can't use to tell them apart. Criteria number 3, onward to that. So in criteria number 3, structures with fewer formal charged atoms are preferred. In each of these 3 cases, they all 3 have the same number of atoms that have formal charges. That is, they all have a negatively charged atom and a positively charged atom, so we can't tell them apart based on that. We come to criteria number 4. Negative formal charges are preferred on the more electronegative atom. Positive formal charges on the less electronegative atom. We look at these structures. In all cases, they have a negative charge on the oxygen, positive charge on the carbon. And so for that purpose, we can say that these 3 are all approximately equal contributors. There will be some subtle difference in contribution based on how far separated the positive and negative formal charges are there, where less charge separation is preferable. So technically the structure right here that I'm putting a star on is somewhat better than the other 2 structures. But based on these 4 basic criteria that we've looked at up top, we can say that the contributions of these 3, we could argue, are relatively equal to one another, because we're really digging pretty deep and down to pretty fine points and minor differences to separate out these 3. So we'll go ahead and deem those as being approximately equal contributions. So we'd rank all of those as equal contributors, but definitely the major contributors are going to be that one on the far left, because that was the one that had the octet. So main thing to keep in mind here is get really comfortable with these 4 criteria and applying them in order, because we're going to use these criteria throughout the semester as our way of going about determining the relative contributions of different structures in resonance. And that's going to be a really critical concept in terms of allowing us to predict how reactions are going to take place, where they're going to take place, how stable or unstable reaction products and intermediates are. We're going to see that resonance is a major factor that determines that, and looking even deeper into that the individual stabilities of the resonance structures are what are going to drive how favorable or unfavorable different structures are. So get very familiar with these, and when you take a look at the resonance worksheet, you will see, particularly on the solution set, some highlights of different ways to tell whether structures are major contributors or minor contributors. So definitely be sure and take a look at that and take that all to heart as you go through.